Last time we learned how to write a composite trapezoidal rule. Okay, and we have come up with the formula which is composite trapezoidal rule. So that was integration a to b f of x dx was equals to summation I is equals to 0 to n minus 1 integration xi to xi plus 1 f of x dx. So we have subdivided ab into n equal length subintervals, and this is equals to, if you apply with the notation that xi plus 1 minus xi, the length of the each ith subinterval is equal to h. So that will be this is equals to, or you can say approximately summation I equals to 0 to n minus 1 xi plus 1 minus xi divided by 2 time f at xi plus f at xi plus 1. So if you take uniformly spaced, so that is going to be is equals to, this is h by 2. So h by 2 is common because it's equal, and if you open it up, the summation f of x naught plus f of x1, the first term, plus second term was f of x1 plus f of x2. Third term, if I want to write f of x2 plus f of x3 plus and so on, plus the nth term is f of x n minus 1 plus f at xn. Now you can see that f of x naught and f of xn means x naught is nothing but a and xn is nothing but b. Except these two, everyone is repeated twice. So f of x1 here and f of x1 two times. F of x2 plus f of x2 two times f of x2. F of x3 plus f of x3 two times f of x3 and so on. So that will be is equals to h by 2 f of a plus 2 times summation I means interior point, right? I equals to 1 to n minus 1 f of xi plus f of f value at t. Right. So this is the trapezoidal rule. If you have been given with the tables x0, x1, x2, xn, and f1, fn corresponding to the data that you can fit into it, and we have seen that going to be exact for polynomial of degree less than or equal to 1. Okay. And we have seen that the error is going to be of the following form. Right? And this is there. Okay, so this is seen in, yes. Okay, so this is the error term. Now we wish to evaluate this example. So last time we have leave this as an exercise. So we want to evaluate 1 by ln 3 integration 1 to 3 1 by x dx. So if you analytically, if you need, so see that is nothing but this is ln x, so ln 3, so that integral value is 1. This integral value is 1. So we want to evaluate this by composite trapezoidal rule with h equals to 1, h equals to 0.5, and h equals to 0.25, and also we want to see the error, how much error is there. Okay, that I is equals to this. So if you look at what is integrand is 1 by x times ln 3. If you compare with a to b, integration a to b is 1, b is 3, and I is to 1. So for the case h equals to 1, the following table will be there. So starting with x naught is 1. So x naught, x1, x2. So x naught is 1 plus is 2, 2 plus 1 is 3. So 1, 2, 3. So you are going to evaluate value of function at these points. These are given by this. Now use the trapezoidal rule. So what the trapezoidal rule says is h by 2 time first value plus last value plus 2 times the sum of the intermediate value. So here the only one. So this is 2 into this. So it is going to be 1.055. Now if you of h equals to 0.5 instead of you are taking 1, means you are reducing the size of step size. Okay, so then you are starting with x naught. So the next value is 1.5, then 2, 2.5, 3. So you are including, means you are subdividing the interval 1 to 2 and 2 to 3 again. Now you mark the values. Okay, you can use the calculator for the same. Now what will be the what will we expect is the value should be more accurate. Okay, though 1.055 is near to 1 only. Okay, so now, so what will be that? I is h by 2 times first value plus last value plus 2 times the sum of these three. So that is going to be 2 times this. So if you evaluate this, it's going to be 1.0125. So it's more closer than this if you refine the partition now. Now, if you go with more number of points here, or if you consider the refinement here, h equals to 0.25, then you are going to add is equals to, so h by 2, so h is here 0.25, 0.25 by 2 time first value plus last value plus 2 times the sum of these values. So that is going to be 1.00125. That's going to be the integral value approximately. Okay, I is approximately equals to this. And that is more closer to 1. So this gives you the idea that if you make the refinement of the partition, earlier partition, that you will get more accurate value than the previous one. Okay, but the thing is, again, this is not exact. Okay, and we are having guarantee that it's going to be exact up to polynomial of degree less than or equal to 1. Okay, right. Okay, so let's move further now. Okay, now if you recall the Newton-Cotes formula, so if you recall the Newton-Cotes formula, means you have been given with a function f. You know that function is a real valued function which is integrable, or you can say at least continuity is there. Okay, and you have the partition with equispaced points x naught less than x1 less than equals to, you can say, and so on, less than equals to xn equals to b. And you have the xi is equals to a plus ih with I equals to 0, 1, 2, and so on. N, h is equals to b minus a by n. Okay, and we have approximated integration a to b f of x dx by integration a to b Pn of x dx. What was Pn of x? So this is going to be given by summation I equals to 0 to n ai, if you recall, that is f of xi. What was ai is integration a to b li of x dx with I equals to 0, 1, 2, and so on. Okay, so this was the formula. So now, so from here only we are getting the trapezoidal rule. Just now we have derived. So similarly, if you take case n equals to 2, so if you take n equals to 2, then you will derive a formula. You derive a formula which is known as a Simpson's rule. That now we are going to derive. So Simpson's rule. What is means what it will tell you is n equals to 2 means means you are going to approximate function by a quadratic polynomial. Now earlier you are for trapezoidal rule you were having you have approximated f by a linear polynomial, right? Okay, p1 of x, right? Now here you are going to make the quadratic polynomial approximation. So what you are expecting this, so previously it was exact for polynomial of degree less than equals to 1. Now what you are expecting is going to be exact for polynomial of degree less than or equals to 2. But unfortunately, you can say fortunately, it is going to be exact polynomial of degree less than or equal to 3. You will look at the error term and we will see why it is so. Okay, and what will be the formula shape here? Okay, right. So now we are going to have the case n equals to 2, and in the Newton-Cotes formula, so you have x0, x1 and x2. So you have the 3 points a plus b by 2 and b. So 3 points are there. So you are starting with the 3 points. Means n equals to 2. N is means whenever you are going to apply the composite Simpson's rule also, you are going to means it is suggested that you are going to make the even number of intervals, you can say, okay, or odd number of points. So n equals to 2 means 3 points here. So if you subdivide the a to b into n equals of parts, so what should be n value should be taking in even number of equals of intervals, you can see, okay, instead of going with odd number of intervals, okay, because it's going to use 3 points at a time, okay, and you want to make keep the continuity structure as well, okay. You are going to join the interval xi to xi plus 1 to xi plus 1 to xi plus 2, so next intervals, okay, right. So we are having Simpson's rule. We are going to derive the Simpson's rule for these points a plus b by 2 and b, means they are symmetrically placed, right? So these points are symmetrically placed, a plus b by 2 and b, okay. We want to determine the formula for these three points. Now note that whenever you are talking about polynomial interpolation, the order of the points, this x0, x1, x2 does not matter much, okay, because of the uniqueness of interpolating polynomial. So whether you take the order a plus b by 2 b or a plus b by 2, you are going to lead with the same interpolating polynomial, okay, right. So we are going to take the order here a. First point is a, second point is b, and third point is a plus b by 2. So this is x0 value is a for me, x1 value is b, and x2 value is a plus b by 2. This is going to be due to the uniqueness of the interpolating polynomial. Now by looking at this, I can certainly write the quadratic polynomial approximation for given function f. So by using polynomial interpolation, what will be f of x is f of a plus f of a comma b x minus a plus is going to be f of a comma b comma a plus b by 2 x minus a into x minus b right? Plus the other term that is going to be the, you can say, error term, that is going to be f a comma b comma a plus b by 2 comma x time x minus a into x minus b into x minus a plus b by 2. See, whether we are writing the Newton's form or we are going to write the Lagrange form, both are the same thing, right? Because of the uniqueness. Okay, and for the simple derivation, okay, then so we are going to consider here Newton's interpolating polynomial for this. So this we are going. This is nothing but the p2 of x. So that is going to be p2 of x plus this error term. Okay, now first we will go for integration. So now this implies integration a to b f of x dx is going to be integration a to b p2 of x dx plus the error term. Integration means you have, again, that's going to be error term. Call that error term. So we are going to calculate this error term separately. So now, so we are going to write this is going to be equal to integration a to b, integration a to b, f of a plus f of a comma b, x minus a time f of a comma b comma a plus b by 2 time x minus a into x minus b dx, that plus error term. So now this is easy to integrate. So that's going to be, first term is f of a time length of the interval, that is b minus a. Second term f of ab, this is x minus a. Okay, so f of ab, so that we have also derived in the trapezoidal rule as well, this term. So f of ab is what? F of b minus f of a divided by b minus a. So that is the formula for divided difference. And this is x minus a whole square by 2. So this is x minus a whole square by 2, upper limit and lower limit, plus f of a comma b comma a plus b by 2 time integration a to b x minus a into x minus b dx. Okay, right. So now we are going to evaluate this now, which we are going to simplify now. This is going to be, so this is here going to be b minus a whole square, right? B minus a whole square by 2. Now one b minus a will get cancelled, and if you sum up first term and second term, what you will get is b minus a by 2 time f of a plus f of b. The first two term will lead to the trapezoidal rule. Now what about the next term? That is going to be f of a comma b comma a plus b by 2. Now integrate this term. Okay, so you can integrate two ways, by using product rule, or you can open this product and then integrate. Okay, so that also we have done during the trapezoidal rule when we are trying to find the error term. So that is going to be, I'm just writing the simplified form of this, the final term. That's going to be, if you recall, this minus b minus a cube by 6. Okay, now you use the recurrence relation for the divided differences, okay, higher order divided differences, and simplify this and verify that this is going to be equals to b minus a by 6 times f of a plus 4 times f of a plus b by 2 plus f of b. Okay, so open this divided difference formula and you can verify the following. Okay, right. So see, you are going to have here, see, if you 2 times use the recurrence relation here, so you are going to cancel with b minus a, you will get cancelled 2 times. Okay, that you when you use the formula, higher order divided differences formula. Okay, right. Now this is going to be the Simpson's rule. Okay, so b minus a by 2. So if you are using it here 3 points. Now what is b minus a by 2? If you look at, that is going to be h, because you are divided into 2 sub-intervals, and this is going to be h by 3 f of a plus 4 times f of a plus h plus f of b. F of b is f of a plus 2h. So that is a plus 2h. Okay, right. Now, so this is because of this coefficient here 1 by 3. This is also known as Simpson's 1/3 rule. Because of the h coefficient, that is going to be 1 by 3. Now, also one more thing you can notice, that here, if you add these weights, so 1 plus 4 plus 1, that is going to be 6, divided by 6. So that's going to be 1. Okay. So, similarly, in the trapezoidal rule as well, if you recall, this is trapezoidal rule. So 1 plus 1 is 2, 2 divided by 2 is 1. Okay, so this is going to be, you will see the similar scenario in the when you use higher degree interpolating polynomials. Okay, when you use this technique. Okay, so now let's work out with the error term now. Okay, okay, so now what is error here in Simpson's rule is going to be integration a to b f of a comma b comma a plus b by 2 x time x minus a into x minus a plus b by 2 into x minus b dx. Now note that this is continuous. It's not a problem. This continuity of this divided difference is not a problem. The problem is w of x. See, x minus a into x minus b is always less than equals to 0. But due to this x minus a plus b by 2 in the factor, what you will observe is wx is less than equals to 0 for x belongs to a plus b by 2 to b, which it takes sign wx is greater than equals to 0 for x belongs to a plus b by 2. And also further you can show that integration a to b w of x dx in this case is equals to 0. So what you can do, so this you can verify. It's very simple. So you have cubic polynomial, and you simplify it and use the integral. That's a one way. Or you can have the alternate way. You just substitute in this integral. So you can use this substitution. Y is equals to x minus a plus b by 2. And take k is equals to b minus a by 2. you take the substitution, then this integral will reduces to integration minus k to k, y minus k into y plus k dy. And this integral is a odd function over this minus k to k, and you can use the definite integral property that is going to be zero. Okay. Verifying this is going to be is not a problem here. Okay. Now, so the very first thing is, since wx is changing sign over the interval a to b, so the mean value theorem is not applicable. That mean value theorem for integral calculus, what we have used in the previous trapezoidal rule, is the same, is not going to be applicable here because wx is changing the sign. So what you can do is you can add one more point or here and use the fact that and use the recurrence relation of divided differences. So this is the same situation like you are writing the expansion for sin x and cos x, right? You are having only odd powers or even powers respectively, right? So here you are going to have in error term. So see, so this term will not contribute much when you are going to have this integral a comma b comma a plus b by 2 and comma, you can say some c, this integral x minus a into x minus a plus b by 2 into x minus b. This integral is 0. So this term will not contribute. So you are going to consider the next term, right? So this is why it means that it is going to be, you can say, exact for polynomial of degree less than equals to 3, because then is going to be approximated by fourth order derivative. Okay, so what I have told just now, just let's see. Okay, so now we are going to use the following recurrence relation now, that if you add one more point, c comma a plus b by 2 comma b comma x is equals to, if you recall, what is that, is f of a comma a plus b by 2 comma b comma x minus f of c comma a plus b by 2 comma b divided by x minus c, if you use the higher order divided differences. Now this will implies f of a comma a plus b by 2 comma b comma x is equals to f c comma a plus b by 2 for any point c in between a to b, you can say. Okay, you can write this one for any point c in between a to b, plus f of this divided difference c comma a plus b by 2, that you can say the next term b x times x minus c. Now this c is in our hand. Okay, c is in our hand. So now, so we can choose c comfortably. Okay, so now if you, this implies integration, so error term, you can say integration a to b f of a comma a plus b by 2 comma b comma x times w of x dx is equals to, so w of x multiplied. Now what is, so here this will be out, right, because this is a constant. And now you know that integration a to b w of x dx is 0. So this term will not contribute anything. So only what you will remain with is integration a to b f, the divided difference c comma a plus b by 2 comma b comma x times x minus c times w of x dx. Now since, see, you can choose this c point comfortably. Okay, so what I will choose here is, I choose, since I know that, see, what is w of x? W of x is x minus a into x minus b into x minus a plus b by 2. Now see, these terms is less than equals to 0. Only because of this is happening. Now if you add W of x into x minus c, what a point I will choose this if I'm going to multiply here by minus c. So I'm going to choose c is equals to a plus b by 2. So once I choose a plus b by 2 c, then this term can always positive x minus a plus b by 2 square it will be, right? So if I choose c is equals to a plus b by 2 implies W of x into x minus c, that is x minus a plus b by 2, will always less than equals to 0 for every x in a to b. And you can apply now mean value theorem for integral calculus. And then you can finally derive the error term. So this implies now error term in Simpson's one-third rule, that's going to be integration a to b f of a plus b by 2. C chosen is a plus b by 2. B a, right? C is a plus b by 2. A plus b by 2. B comma x time W of x into x minus c, that is x minus a into x minus b into x minus a plus b by 2 whole square dx. Now use the mean value theorem because this is going to be continuous and this does not change sign. And this will be once you assume the smoothness, right? F, this is continuous and f is 4 time differentiable. So this will be something like 4th time derivative at some z by 4 factorial. That's going to be converged to this. Okay? Right? And what will be here is this is going to be the term that is going to be integration a to b x minus a into x minus b into x minus a plus b by 2 whole square. Now use the same substitution here. X minus a plus b by 2 is y and k is equals to b minus a by 2. Then you can simplify this integral. So you can use the substitution here. Y is equals to x minus a plus b by 2 and with k equals to b minus a by 2. So error term is equals to 4th derivative at some point in between an interval a to b divided by 4 factorial. Limits are going to be x equals to a, you have a minus this is 2a, so that is a minus b by 2, so that is minus k, 2 plus k, and what you will have is y plus k into y square into y minus k dy. You can see here when you have, so you can write this as x minus a you can write as in the term of y and k. Okay, so similarly for x minus b. So what is y is, that's very simple here. What is y plus k? If you want to write, that is going to be x minus a plus b by 2 plus b minus a by 2. So that is going to be minus a by 2 and minus a by 2 will get cancelled. That is going to be x minus b. Now if going to y minus k, it's going to be x minus a. Okay, and now this integral can be solved easily than the previous one. Okay. Similarly, y minus k, you can show that that is going to be x minus k. And then further equals to fourth derivative by 4 factorial. You have minus k to k. So y square into y square minus k square. So that is going to be y to the power 4 minus k square times y square dy. So even function, you can use the definite integral property and you can solve this. Then, so I'm going to write the final term here. That's going to be minus a fourth derivative at eta by 90 times b minus a by 2 to the power 5. Okay, right? So this is where you have the Simpson's 1/3 rule now. Now, by using this error term, and you can use the formula for Simpson's 1/3 rule on in the interval a to b, you can write down the composite Simpson's 1/3 rule now. Okay, so let's write down. It's the same way. So you have composite Simpson's 1/3 rule. So you are subdividing a to b into the subinterval xi to xi plus 1 with I equals to 0 to n. With xi is equals to a plus ih, I is equals to 0, 1, 2, n, h is equals to b minus a by n. And then you are on every interval, you are applying the Simpson's 1/3 rule, and then you can write the composite. Now, so I'm choosing here n is even. So you can write the compact form for Simpson's 1/3. Okay, because many times and even means number of points are odd. So many times you don't know the function definition. Okay, so you may not be able to get the value of the function at the midpoint, because on every point, so when you write a to b f of x dx, that's going to be summation I equals to 0 to, this is going to be n minus 1 here, n minus 1 time integration xi to xi plus 1 f of x dx. And if you use this Simpson's 1/3 rule, that's going to be approximately, that is summation I equals to 0 to n minus 1. That is, you have, this is going to be xi plus 1 minus xi by 6, b minus a by 6, right? So b minus a by 6 time f of a plus 4 time f of a plus midpoint value. So let me write. This is equals to xi plus 1 minus xi by 6 time f at xi plus 4 time f at the midpoint value xi plus 1 by 2 plus f at xi plus 1. And now you take, these are uniformly spaced, so this is going to be xi plus 1 minus xi on each interval, that is going to be h only, right? So this is going to be h xi plus 1 minus xi. So see here on the previous, so here xi plus 1 minus xi was means in the previous case h was b minus a by 2, if you recall. Okay, means because it uses 3 points. So it is uses 3 points. So xi plus 1 minus xi by 2 will be the h for that case. Okay, if you compare it with the, okay, so if you compare with the previous methods, xi plus 1 minus xi was 2h actually. Okay, so this is going to be 2h by 6, so that is going to be h by 3. That's the first thing. And now if you open this here, what you will get is f of a plus f4 time f of x naught plus x1 by 2 plus, so you have to write this for all the terms here, f of x naught plus 4 time f at, you can say that is going to be beta, you can say, I can just call it as beta I or beta naught, okay, plus f at x1 when you take I equals to 0. What is beta naught and all that we are going to write now, okay, plus f at x1 plus 4 time f at beta 1 plus f at x2 plus and so on. Now that's going to be is equals to h by 3 time. So f of x naught will not be seen in between anywhere like f of xn. Okay, so f of x naught plus f of xn. Okay, right. Now plus 4 times summation f at beta i's, I is equals to 0 to you have, this is going to be n minus 1. So because beta naught, beta n minus 1 plus 2 times summation I equals to 0 to, I equals to 1 to n minus 1 f at xi. So these all terms repeated, f of x1, f of x2, f of x3, f of x4, internal points you can say. These are repeated 2 times. What are beta i's? So beta i's are xi plus 1 by 2. Okay, right. Now, okay, any doubt here? Okay, so f of x naught and f of xn will not be occurring anywhere else in between. F of x1 and f and so on, f of xn minus 1 will be repeated twice, and the function value at the each midpoint of the interval xi to xi plus 1 are going to be means like 4 times. Okay, now if you look at the table, okay, if you look at the table, why we have decided n is even or n is and number of points are odd, then see what is h here. This h is the interval length x naught to x2. Okay, this h length. So if you look at the table, if I want to write directly from the table, what are the, so you have x naught, f naught, x1, f1, x2, f2, x3, f, x4, f4, and so on, xn minus 2, fn minus 2, xn minus 1, fn minus 1, xn minus n, fn. So when you want to use the Simpson's rule for the directly for the table, so what will be the formula here? That's going to be, so what is h? First thing is h to decide. H is going to be, so you are going to x to x2, x2 to x4, x4 to x6, and so on, and xn minus 2, xn. And then, so here they are uniformly spaced, x1, x3, and xn minus 1 are the spaced, these values, spaced values. Means these are the midpoint of this each interval. So h is equals to x2 minus xn, or you can say xi plus 2 minus xi. Okay, so if the space here is x0 to x1, you are calculating that h. So x0 to x2 is 2h, you can say. Okay, that's the first thing. The second thing is, what will be the formula? That integration x0 to xn f of x dx is approximately h by 3. What is that h is? Xi plus 2 minus xi time f0 plus fn. So these midpoint values, some of these midpoint values are going to be multiplied by 4 and add. And some of these f2, f4 and so on, fn minus 2 are multiplied by 2 and then add. Okay, so these are, you can say, odd, right? These are the odd places, right? f1, f3, f5 and so on. And these are the even places, f2, f4, f6 and so on. Okay, so with this in mind, what we can write is, that is going to be, you have this 2 times summation I is equals to 2 to n by 2. If n is even, f at x 2i minus 2. So you are multiplying with odd even places, right? 2 times and sum up to n by, so 2n by 2 is n minus 2. So xn minus 2 till xn minus 2 you are evaluating, plus 4 times summation I is equals to, just going to next page. So what is there is x0 to xn f of x dx is equals to h by 3 time f0 plus 4 time plus 2 time summation I is equals to 2 to n by 2 f at x 2i minus 2 plus 4 time summation I equals to 1 to n by 2 f at x at 2i minus 1 plus fn. So this is the formula when you look at the table, when you don't know the function value. So this is how you will proceed. But if the function is given, you can refine it by adding. So you, instead of taking x0 to x2, you start with x0 to x1 and evaluate the function value at the midpoint of this. That's a separate thing. Okay, right. So this will give you the composite trapezoid, composite Simpson's 1/3 rule. Now, so we can derive the now error term. Likewise, we have derived for the composite trapezoidal rule. So we are going to proceed in the same way. Now, error in composite Simpson's rule. So 1/3 rule we are talking about. So what is that is? That's going to be, so error term on xi to xi plus 1 was minus f fourth derivative at, say, eta I by 90 time b minus a by 2 to the power 5. So b minus a is xi plus 1 minus xi. So that is xi plus 1 minus xi by 2 to the power 5. Okay, so xi plus 1 minus xi by 2 will give you the h. So that is going to be h to the power 5, or you can say, okay, right. Okay, h to the power 5 will be there. So if you take uniformly spaced, so this is going to be minus f fourth derivative eta I divided by 90 times h to the power 5. Okay, now error term on the interval a to b, that's going to be minus, so h to the power 5 by 90 is same for every, so summation, right? So summation error on xi to xi plus 1, so you have this summation I equals to 0 to n minus 1, error term on xi to xi plus 1. Now you substitute this here, so that is going to be minus h to the power 5 by 90, because it's going to be the same, times summation I equals to 0 to n minus 1 f fourth derivative at eta I. Now, since f fourth derivative is continuous on the interval a to b, so you can find a zeta. So you can again apply the intermediate value theorem here. So you have f fourth derivative is continuous on closed interval AB. So let m is equals to maximum of f fourth derivative and small minimum, and capital M is maximum of f fourth derivative over the interval a to b we are talking about. So you have, this is small m less than equals to f fourth derivative x less than equals to capital M. Now if you have, instead of x, eta I and summation I equals to, so this will implies, so if instead of x you have eta I as well, and if you vary from I equals to 0 to n, you have m times n less than equals to summation I equals to 0 to n minus 1 f fourth derivative at eta I less than equals to m times n. Now you can bring on this side. Now you can use intermediate value theorem, which says that there exists a point z such that f fourth derivative at z is equals to 1 by n times summation I equals to 0 to n minus 1 f fourth derivative at eta. Okay, so use this result. We have already used a similar result in trapezoidal rule as well. Okay, so you use this, so summation, this will be replaced by n times f fourth derivative at z. So this result will imply, this implies error on a to b sorry, error on AB in Simpson's rule is equals to minus h to the power 5 by 90 n time f fourth derivative at some c. So what is n is b minus a by h, right? So one h will get cancelled. Okay, and but b minus a, see this n is what, b minus a by h, but b minus a by 2h actually. right? So because n is, so h is equals to b minus a by n, if you recall. Okay, but here we are using a midpoint as well. So in each interval you are having by 2 as well. So you have by 2h. So you are going to be is equals to minus s to the power 4 by 180 times b minus a at fourth derivative at z. Okay, so h is equals to b minus a by 2n. Okay, right. Or you can say 2h is equals to b minus a by n. Okay, right. So this will give you the error in composite Simpson's one-third rule. So let's see the comparison between trapezoidal and Simpson's one-third rule now. Okay, and also you can means there are two more basic rules. One rule is rectangle rule. Another rule is midpoint rule. Okay, so what is happening here is, so so let me give you a brief description, okay, for what is happening in rectangle rule, what is happening in midpoint rule. Okay, so let me write this. Okay, so in rectangle rule, I'm just going to tell you what is the rectangle rule. So that actually a Riemann sum, if you recall. So you have the here, so let's say A, this is P. So you take this either the left hand point or you take the right hand point. So there are two rectangles you can form if you are only looking at into A to B. So what will be the area under the curve integration A to B? If you approximate by rectangle, lower part is going to be b minus a into f at a. Similarly, if you take the upper means that upper rectangle means above the curve, that is going to be f of p into b minus a. Okay, so basic rectangle rule you have is this is integration a to b f of x dx is approximated by f of a into b minus a. Either this or by using this. So you will have, this will be the error here. So this will be the error if you use the lower part. So if you use the upper part, the error will be this much. And then, and you also can see that this rectangle rule is, if you talk about the error term here, okay, if you talk about the error term, what will be the error here is, means you are approximating by a constant polynomial, right? F of a. Constant polynomial means 0 degree polynomial. So what will be the error term is f of, so you are going to, so if you talk about the 0 degree polynomial, in the 0 degree polynomial means you are using the left hand point a. So a comma x times x minus a. That will be the error if you look at the Newton's interpolating polynomial. So that is going to be this integration a to b dx. Now you can use the mean value theorem for integral, because since this is continuous, you are using the continuity of the function. This will be continuous, and this remain. This does not change any sign. So you can use the mean value theorem here. That is going to be f of a comma c for some point c in between open interval a to b, right? Integration a to b x minus a dx. And if you assume that f is differentiable once, so that is going to be f dash at some eta by 1 factorial. So that is x minus a whole square by 2. And if you put upper limit minus lower limit, so you will get b minus a whole square by 2. Okay, so this is going to be divide, yeah, right. Okay, so this is going to be f dash at eta divided by 2 times h square. So this is going to be exact for polynomial of degree less than equals to 0 only. So only for constant degree polynomial. Okay, but and you similarly you can write the composite rectangle rule. Okay, so this implies the rectangle rule, basic rectangle rule is exact for only for constant degree polynomial, means 0 degree polynomial. Okay, right. So by using this basic rectangle rule, you can write the composite rectangle rule. Means we are creating the partitions, so that you have seen that actually this Riemann integral, Riemann sum, and upper sum and lower sum, you can use the refinement of the partition. And then if you use the refinement of the partition, and as n tends to infinity, this actually tends to the area of the integral, means like integration a to b f of x dx. That is you have not already known from the your calculus part. Okay, right. So similarly, you can write the composite rectangle rule. So if I want to write composite rectangle rule, that is integration a to b f of x dx is equals to summation I equals to 0 to n minus 1 f of integration xi to xi plus 1 f of x dx. Now this is going to be by each length of the subinterval xi plus 1 minus xi into the f value at the left hand point xi summation I equals to 0 to n minus 1. Now if you take xi plus 1 minus xi is equals to n, h, okay, so that is going to be h time summation I equals to 0 to n minus 1 f at xi. Okay, right. So this will give the composite rectangle rule. And in error, if you go with the error term, what you will get is f dash at eta by 2. So eta I will be there. So one more h will get cancelled. So you will have the O of h only. So if you talk about the error term, is equals to going to be at f dash at eta, this h square by 2 times summation I equals to 0 to n minus 1 f dash at eta I. And now you use the intermediate value theorem and continuity of f dash. There will be some point in z. So this is going to be is equals to h square by 2 times n time f dash at eta. What is n is b minus a by h. So that's going to be b minus a by 2 f dash at eta time h. Now, if you look it back and see, whenever you are talking about composite, you have reduced by 1 power of h. So earlier in the basic one was h square. In here we are reducing with h. Similarly, for the Simpson's rule, earlier for the basic one was h power 5, but now it is reduces to h to the power 4. Okay, right. Similarly for trapezoidal as well. So for trapezoidal, you have been started with F. For the basic trapezoidal rule, you were having h cube. But then when you talk about the composite trapezoidal rule, it reduces to h square. Okay, right. Okay. Another basic rule, what I have also given in your practice sheet. Okay, that's called midpoint rule. Okay, so what is midpoint rule is saying is, so if you look at here, the curve A, this is B, this is your f of x. Now, what you will do is, you look at the midpoint A plus B by 2. So you will have the f of A plus B by 2. And you draw the line parallel to this. So, earlier you were having either this or this in the rectangle rule. Okay, so again, see, you are again approximating f by a constant degree polynomial, but at the point a plus b by 2 now. Okay, so how will it help you? Whether it will remain the same or it will improve. Okay, so if I this is a basic midpoint rule. So what is tell you is integration a to b f of x dx is approximated by, so that is f of a plus b by 2 times b minus a, the area of the rectangle, and this will be the error. Now look at here. So if you look at geometrically, okay, let's look at the straight line. Let's take this line, and let's say this is a and this is b. And if you look at the midpoint, this is, let's say, a plus b by 2 midpoint. You have this point. So if you draw the rectangle, so what will happen here? In this case, this includes, right? This includes this part, but this excludes this part. So, but due to the symmetry, this and this has the same area. So what will happen is, what will it give you is, that means that area is covered here. Okay, because of the symmetry here. Okay, because of the symmetry about the point a plus b by 2. So area above this and this will be the same. So this is the beauty of midpoint rule. So instead of taking the left hand point or right hand point, if you take the midpoint of the interval, so it is expected to be exact up to 1 degree polynomial. Okay, it is expected. Okay, whether it is or not, that we are going to see. Okay, right. So what you can now do is this, you can show that what will be the error term here. So see, this is going to be what is error term. If you look at error term, if you approximate by a constant degree polynomial, what will be the error term is f of, you are using the point a plus b by 2, right? So that is going to be you are going to use the point a plus b by 2, and so f of a plus b by 2 time b minus a. So yeah, this is going to be length of the, yes. So this is going to be f of a plus b by 2 comma x time x minus a plus b by 2. Now what will happen now? So you can so now if you error term here is going to be integration of this. Now see, you cannot integration a to b. So now you cannot, still again you cannot apply the mean value theorem for integral, because this term will not have the same sign over the whole interval a to b. This is continuous, but this will not remain the same sign. So again, you will observe the similar technique what you have done for Simpson's rule. Okay, that this is going to be I mean you're going with the you are going to use the recurrence relation of the divided differences. Okay, and also note that integration a to b x minus a plus b by 2 dx, you can also show that this is going to be 0. Okay, this is going to be the 0. So, and then in totality, I just I'm going to give you the final expression error term, and by you after including one more point site c comma a plus b by 2 comma x, and use the recurrence relation, then you can show that this is going to be a second derivative at eta by 24 times b minus a cube. Okay, right. So, sorry. So this clearly tells you that this is what if I want to write in the terms of h is f second derivative at eta h cube by 3. Okay, right. What is h is here? What you have taken is b minus a by 2, because you have subdivided into two intervals, a to a by 2 and a plus b by 2 to b. Okay, so now similarly you can go with the composite midpoint rule now, and there you will see one h will reduce. Okay, one h will be reduced, and what you will get is, oh, here h is what only sub, right, 1 only, b minus a only, h cube by 20. Yeah, that is fine. Okay, so now if you generalize this for composite midpoint rule, then what you will have is I'm writing directly the final term, that is, and then I will close here. Integration a to b f of x dx is equals to summation I equals to 0 to n minus 1, approximately I'm writing now. That is going to be xi plus 1 minus xi time f value at the midpoint of the xi plus xi minus 1, xi plus 1 by 2. And what will be the error term? Will be b minus a by 24 f second derivative at z h square. Okay, right. So here we will stop now. Okay, and then in the next session we are going to see which one is better. Okay, we will compare, and we will come to some conclusion about it. Okay, so let's take your doubt. Previous page. Okay, here. Yeah, Prithvi. Because you have only interval a to b now. So h is, we are only taking the interval h equals to what is h is nothing but the length of each sub interval. So only interval you are using is a to b. So h equals to b minus a. Okay, right. Okay, thank you.